In last few videos, we talk about the kernel tricks where we can apply, we can find the solutions even we have the huge dimensions of the new features based on the existing features. Okay, for example, if the original data has only two features, I think we have one example here, right? Two features, we can transform up to we have the six features, right? Six features. But what if we have infinite many features? Can we do that? The answer is yes. So that trick is called the Gaussian kernel. Okay, polynomial kernels gives D polynomial transformation. Okay. What if can we have the infinite dimensional space? Infinite many feature space. Okay. So the answer is yes. Yes, we can. The answer is given by the kernel Gaussian kernels. So it's by the Gaussian kernel. Okay. The Gaussian kernel is a function. Kernel function is a transformation from the feature space. Suppose you originally have the D features. Now you want to convert to a space with infinite many features. Okay, such that the kernel function is defined by exponential negative x minus z divided by 2 sigma square. Okay, so this sigma square is the hyperparameter. You can tune. Okay, and I think I need more space here. So remember, think about the previous time we calculated the trick, the kernel tricks. Apply this kernel tricks. Even we have the D feature space, the actually calculation only is n by n. So similarly is here. For example, even you have the infinite many. Suppose you have the D. Suppose you only have one feature. Okay, then the phi x is transformation is exponential of the negative x square over sigma square, 2 sigma square, multiplied by the polynomials with the constant term, first order term, second order term, third order term, and so on. For example, you have the nth order term, m order term, and so on. So it's infinite many vector, a vector. infinite many term. And for any vector, note the phi x, a vector, transform times phi z. The kernel part is a series, converges to this kernel function, kxz. Yes. So, so here is one example. At this point, it may not be best to think the points in the high dimensional space. It's no longer useful intuition, but instead we just working on the. You can think the kernel K is a measure how similarity close to each other 2 points together. Okay, so you can think kernel is a measure that measures the differences for similarity or closeness 2 points to each other. Okay, and then if we apply this kernel function, our function, regression function, will equals to the linear combinations of this k xi to z. Okay, so once you we can find the solutions for this a vector. We find the linear combinations of the k normal densities. We can find the solution. You can think this is so this weights ai is the coefficients of linear combination. So you can think this is the Gaussian's basis for this distribution. For example, in this plot, we fit the Gaussian kernel to some regression problem. I think in this case, we have the 4 training points. This is x1, x2, x3, x4. Okay, so here we have the 4. So your regression function will be the linear combination of 4 terms. The good thing is, it's very popular. Okay, it's a very popular technique in practice. It's mainly due to the regression function is infinitely many smooth. The HA given here is smooth in infinite order. So it somehow behaves. Similar to k nearest neighborhoods. But smoother. So this k, you can think of this can be tuned as a sigma, right? If your k is 1, your sigma is small. If your k is large, your sigma is large. Okay. It has much less variations than polynomials. Features. You can think the training point is a vote for a value for z. Training point. As vote for point z. Closer will get more points closer to z, implies more votes, more weighter vote. Okay. So the standard kernel function assigns more weight to the training point vector that is roughly the same direction as z. By the contrast, the Gaussian kernel assigns more weight to the training point near the z. Okay. And the hyperparameter is this sigma. So sigma is you can control the trade-off between the Bayes and the variance. You can use validation to choose the variance. To choose hyperparameter. Sigma. Okay. The larger sigma, wider Gaussian. And smooth H. More Bayes, less variance. Okay, you can think it's like a k nearest neighborhood. If we only use one nearest point to label the point, it have more Bayes. It has smaller Bayes, but has high variance, right? So if you use a bunch of the points nearby to label the point, so your model will be has low variance, but has little bit more Bayes. Actually, we have another example, last example we can show here. So this is we apply the Gaussian kernels to the support vector machine. Okay, the decision boundary is a soft margin support vector machine with a Gaussian kernel. So you apply this infinite many feature space. Observe that in this example, the true decision boundary is generated by this function. The black line here is the true decision boundary, and and the Gaussian kernel smoothing support vector machine gives very reasonable decision boundaries. Actually, there are many other kernels, like Gaussian kernels, are defined directly as kernel functions without worry about the basis function, feature function phi. But not every function can be kernel function. A function is qualified to be a kernel function if and only if it guarantees the positive definite of the kernel matrix for every sample point. There is an elaborate theory about how to construct valid kernel functions. Probably in this course, it's enough to know the polynomial kernel and the Gaussian kernel are two most popular ways to construct kernel tricks. Okay, I think that's all I want to talk about today. Thank you.